Well, um, you know, before we drift too far into the deep glow of the cosmos, let me ask you something. Something that, lingers in the mind long after the question has been spoken. Have you ever wondered what it truly means to see across time? To look at a faint red shimmer in the dark and realize, well, realize you're not just looking at a star or a galaxy, but at a memory. A memory more than 13 billion years old. Because with the James Webb Space Telescope, this great golden eye hanging quietly at L2, we're not just observing distant light, we're touching the past. And the thing is, every new image, every new detection, seems to whisper the same message. The universe is bigger, older, stranger than we ever dared to imagine. Not just bigger in size, but bigger in possibility. Bigger in the ways it challenges us. You see, JWST has opened a doorway into epochs where galaxies were supposed to be tiny, dim, fragile things. And yet, there they are, bright, massive, fully formed, far too early. It's not just data. It's a reminder that, our models, our neat diagrams of cosmic evolution, may only be the surface of something deeper. So what does it mean when the universe refuses to fit inside our theories? What does it say about us and about the story we're still learning to read? Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple, to help you drift off to sleep while exploring the wonders of science. And, if you're listening out there, just drop me a little sign in the comments. Maybe tell me what the night sky looks like from where you are. It's always fascinating to see who's joining us from all around the world. So let's continue. And, when you look at the night sky, there is this quiet illusion that everything is close, that the stars form a kind of dome just above our heads. Well, you see, for most of human history, we lived inside that illusion. We thought the universe ended where the stars stopped shining. But today, standing here in the early days of the 20th century's successor, in the age of the James Webb Space Telescope, we are finally beginning to understand the staggering truth. The universe is not just vast, it is incomprehensibly vast. And that idea begins with a number so extraordinary, so large, that it almost feels like a joke whispered by the cosmos. 93 billion light years. The strange part. The part that seems almost ridiculous is that the universe is only around 13.8 billion years old. So, how can something that young be so enormous? How can the observable cosmos stretch across a diameter nearly 7 times larger than the distance light could have traveled since the beginning of time? And, the answer lies not in motion, but in something profoundly subtle: the stretching of space itself. Well, you see, when light began its journey, back in those earliest moments after the Big Bang, space was smaller, tighter, almost pressed against itself. The galaxies that emitted that ancient light were far closer to where we stand now. But as the light traveled, space expanded underneath it, pulling the galaxies away, dragging the photons across a growing tapestry. The light kept moving, but the fabric it moved across kept stretching. And that is why the observable universe is so much larger than its age suggests. Imagine drawing tiny dots on a balloon. As you inflate it, the dots drift apart. None of them move across the surface. The surface itself enlarges. So, if a photon began its journey across that balloon when it was small, by the time it reaches your eye, the balloon may have become enormous. The distance it seems to have crossed is far larger than the light could cover on its own. This Well, this is the deep reason our observable universe spans 93 billion light-years. And, the phrase observable universe matters, because we are not seeing everything. We are seeing only what light has had time to reach us from. Beyond that sphere lies a cosmic ocean forever hidden, not because the galaxies are unreachable in principle, but because the expansion of space has carried them away faster than light can bridge the gap. And that is one of the great ironies of cosmology. The universe may be infinite, or it may simply be larger than we can measure, but we will never know the true scale because the horizon of visibility expands slower than the universe itself. And the light we do see, the faintest, the most ancient, the oldest whispers of creation, arrives stretched, tired, elongated. It left its source as ultraviolet or visible light, but by the time it reaches us, the expansion of the cosmos has dragged its wavelengths into the infrared. And that is where the James Webb Space Telescope becomes our enormous advantage. Well, you see, the James Webb is not just another telescope. It is a time machine. And, in a literal sense, because it was designed to see the stretched, reddened light from the earliest galaxies, the Hubble telescope, magnificent as it is, could not see deep enough into the infrared. The earliest galaxies remained invisible, hidden behind the curtain of cosmic expansion. But Webb looks where Hubble could not. It listens to ancient light in the wavelengths where the past still speaks. And that is why the number 93 billion light-years suddenly feels less like a statistic and more like a doorway. Because once Webb opened its golden eye, it began revealing objects whose light has traveled across almost the entire width of that cosmic sphere. Galaxies so far away, their photons began their journey when the universe was less than 2% of its present age. So, when we say Webb lets us look across 93 billion light-years, what we truly mean is that it lets us look back across 13 billion years of time. The comped scale of this becomes overwhelming if you pause for even a moment. The galaxies we see at the edge of the observable universe are not just distant. They are ancient, frozen in time, fossilized in their infancy. And what Webb shows us is not just their shape or brightness, but the truth that the universe we thought we understood is more complicated, more chaotic, more dynamic than our models predicted. And, that understanding begins with a simple paradox. If the universe is 13.8 billion years old, why can we see light that appears to have traveled more than 13 billion light-years? The answer, again, is expansion. The galaxies that emitted that ancient light were once very close to us. The light began its journey across a much smaller universe. But as the cosmos expanded, the distance between us grew and grew and kept growing, even as the photons pressed onward. When the light left those galaxies, they might have been just a few billion light-years away. Today, they may be more than 30 billion. Well, you see, this means that our observable universe is like a bubble whose radius is set not by the age of light, but by the combination of light's travel and the stretching of space-time. And that makes the 93 billion light-year figure not a measurement of how far light has traveled, but a measurement of where the galaxies are now, after a lifetime of drifting outward. And when you look at it that way, the cosmos becomes something almost alive, growing, changing, carrying galaxies on its expanding skin. The universe is not static. It has never been static. Even right now, at this moment, the space between galaxies continues to grow. We grow older, clocks tick, galaxies drift. And, the rate of that drift is not constant. In the early universe, expansion slowed as gravity tried to pull everything back together. But in recent cosmic history, something strange has happened. Expansion has begun to accelerate. Space is stretching faster than before. The more the universe grows, the faster it grows. And this accelerating expansion makes the horizon, our limit of visibility, an ever-shifting, unreachable boundary. Well, you see, this sets the stage for an astonishing truth. Every galaxy we observe today, every fleck of ancient light Webb detects, is a participant in a cosmic dance between gravity and expansion. And the galaxies at the farthest edge of the observable universe are special. Their light is stretched, slowed, cooled, aged. It has journeyed across a universe that has changed beneath it. It is not just old light, it is historical light. And thinking about this brings us to a gentle realization. When Webb observes a galaxy whose redshift places it near the age of the very first stars, we are not just collecting data. We are watching the unfolding of the universe's own autobiography. The photons arriving on Webb's mirrors tonight left their home galaxies before Earth existed, before the Sun existed, before our Milky Way assembled itself. These photons began their travel across a universe of dark hydrogen and quiet voids. And, by the time they reach us, they are stretched into deep red and infrared wavelengths, as though time itself has softened their voices. And, this is why the James Webb Space Telescope was designed as an infrared observatory, not just technically, but philosophically. Because the earliest chapters of the universe are written in infrared. The visible light of those ancient galaxies has been drawn out like taffy, wound slowly into longer wavelengths by the expanding cosmos. Only a telescope like Webb, with its chilled instruments and golden mirrors, can read those stretched-out signatures. Well, you see, that is why the observable universe appears so immense. Not just because light travels, but because space itself grows. The 93 billion light-year diameter is a measurement of becoming, not being. A measurement of what the universe has done to light over billions of years. And that gives our observations a kind of emotional weight. Because we are not seeing some distant, unreachable realm. We are seeing the universe as it once was, long before memory, long before stars had metals, long before galaxies even knew how to spiral. And noticing that, really noticing it, leads us toward the next question. If Webb can see light from the very first % or 2 of cosmic history, then what exactly has it found there? What galaxies emerged in that primordial darkness? How bright were they? How massive? How strange? And, well, among those discoveries is one that has already challenged everything we thought we knew about the early universe. A galaxy whose light began traveling when the cosmos was just a few 100 million years old. A galaxy so distant that its light is stretched by a factor of more than 15. A galaxy called MOM Z14. And that is where our journey must go next. Toward the galaxies that formed at the dawn of time, and the mysteries they reveal about how the universe built itself. And, when we follow that faint thread of ancient light into the deeper dark, right where Chapter 1 left us standing beside the edge of the observable universe, we encounter something almost unbelievable. Well, you see, the James Webb Space Telescope has revealed many distant galaxies. But there is one, just one, that seems to pull the fabric of cosmology taut, as though the universe itself is whispering a riddle we have not yet learned to answer. And that Object is MOMZ-14, a galaxy born when the cosmos had lived through barely 2% of its long and drifting lifetime. Imagine the universe as a child, an infant, really. Only 280 million years old. We grow older. Clocks tick. But in cosmological terms, 280 million years is a first breath, a first stirring. Stars had just begun to ignite. Darkness had only recently surrendered to the first hints of starlight. And yet, somehow, in that fragile dawn, MOMA Z14 was already shining with astonishing brilliance. So, the question becomes, how can something so young, so early, be so impossibly bright? Well, you see, brightness in astronomy is not just about visibility. It's about mass, about structure, about how many stars burn inside a galaxy's heart. And when Webb captured the elongated, deeply reddened fingerprints of MOMI Z14, it wasn't just detecting a distant smudge. It was detecting a challenge, a contradiction, a beacon from a time when galaxies were not supposed to be this large, nor this organized, nor this luminous. And, to understand why, we need to understand something called redshift. That word, redshift, sounds technical, almost cold, but its meaning is beautifully simple. As the universe expands, light is stretched along with it. The wavelength grows longer. Blue becomes red. Red becomes infrared. And for the earliest galaxies, the light is stretched so dramatically that it falls far beyond what human eyes can ever see. That is why Hubble could not capture them. They were invisible not because they were faint, but because their light had been pulled into wavelengths Hubble was never designed to detect. Webb, though. Webb listens to the universe differently. It listens in infrared. It listens in the language of stretched light. So, when it saw MOMI Z14, it wasn't merely seeing across distance, it was seeing across time. The galaxy's redshift, 14.44, means its light has been pulled to nearly 15 times its original wavelength. And that number, that stretching, tells us how far back in history the signal began. And, that is why MOMI Z14 feels less like a discovery and more like an invitation to rethink everything. According to our cosmological models, galaxies at that age should be small, fragmented, chaotic. They should hold a few clusters of newborn stars, flickering into existence for the first time. They should not glow like cities beneath a cosmic night. They should not radiate with the strength of 1 billion suns. And yet, well, MOMI Z14 does. So, what could possibly explain that? Did stars form faster then? Did gravity sculpt early matter more efficiently? Or are our models simply too modest, too cautious, too rooted in assumptions shaped by the later universe? The truth is, we do not know yet, and that uncertainty is strangely thrilling. Think of this galaxy as a fossil from a time when the universe was still learning how to build. Its stars might be among the first generations, massive, hot, short-lived. They could be rich in primordial hydrogen and helium, untouched by heavier elements. And, if these stars were enormous enough, brilliant enough, the whole galaxy could shine fiercely even when young. But, well, there is another possibility. One that sits quietly in the back of every astronomer's mind. What if MOMI Z14 hosts a black hole at its center? A black hole that grew far more rapidly than expected. A black hole feasting on matter, igniting radiation, brightening the galaxy from within. This idea is not just speculation. It is consistent with several other discoveries from Webb. small galaxies with outsized luminosity, too bright to be explained by stars alone. And that leads us toward yet another puzzle. Black holes at this stage of the universe should not be big. They should be seeds, tiny remnants of the first stars, not giants, not engines powerful enough to illuminate galaxies. So, if MOMI Z14 does contain a central black hole, then something extraordinary happened. A growth spurt, a collapse event, or a kind of physics we still do not fully understand. And, well, this is where the story becomes more philosophical. Because each time we try to fit MOMI Z14 into the neat boxes of our models, the edges begin to fray. It's not that our models are wrong. It's that the universe is more inventive than we imagined. It builds faster. It builds brighter. It builds earlier. And that is the beauty of discovery. Well, you see, the early universe was not a calm place. Gas clouds crashed together. Dark matter sculpted invisible frameworks. Radiation from the first stars carved ionized bubbles in the surrounding darkness. Everything was in motion. Everything was unstable. Yet from that chaos emerged structure, delicate at first, then bold, then defiant, like MOMI Z14. And perhaps that is the real lesson this galaxy teaches us. That formation in the early universe was not a gentle unfolding. It was explosive, accelerated, urgent. Stars ignited with reckless abundance. Gas cooled rapidly in dense primordial clouds. Gravity acted with a rawness we do not see today. And so, galaxies grew faster than our models predict because the conditions of that era were unlike anything the modern cosmos can reproduce. And, maybe that is why Webb keeps surprising us. We built simulations based on the universe we see now. But the universe that existed then played by different rules. The question then becomes, what were those rules? What physics governed the first 2% of cosmic time? What processes shaped galaxies like MOMI Z14 into their luminous, unruly brilliance? And answering that requires more than observation. It requires humility. It requires accepting that our theories, elegant as they are, may not capture the full complexity of the universe's earliest chapters. And, this is where MOMI Z14 stands as both a puzzle and a promise. Well, you see, if a galaxy this bright existed so early, then the path from the first stars to the first galaxies must have been far shorter than we expected, or far more efficient, or far more chaotic, or, well, perhaps all three at once. And that means rewriting parts of our cosmic timeline. It means adjusting how we think about star formation, gas cooling, dark matter collapse, and the interplay between early radiation and early structure. And the deeper you think about it, the more astonishing it becomes. Because the galaxy we see now in Webb's mirrors is not MOMS Z14 today. It is MOMS Z14 then. A frozen moment. A preserved memory. A glimpse into the infancy of everything that ever existed. So, when we study it, we are not studying an isolated object. We are studying the universe learning to build itself. The universe discovering architecture. The universe shaping the first scaffolding upon which all later galaxies, including our Milky Way, would be assembled. And, that is why this detection matters. Not just for astrophysics, but for philosophy. It reminds us that the universe grows not by rules alone, but by creativity. It stretches, invents, experiments. Well, you see, as we move forward into the next chapter of this story, MOMI Z14, becomes our guide into the deeper mystery of redshift and light itself. Because this galaxy is visible only because its ancient photons survived a 13 billion year journey, stretched and thinned and cooled by cosmic expansion. And that invites a new question. What exactly happens to light as the universe expands? How does redshift carry history? How does stretched light become a cosmic memory? And to understand that, we must go deeper into the nature of light, into the fabric of expansion, into the strange way time itself inscribes its fingerprint onto every photon. And so, our journey must continue into the very heart of redshift. And, when we step from the luminous mystery of Momi Z14 into the deeper question it quietly gestures toward, we find ourselves confronting something even more fundamental. Well, you see, behind every ancient galaxy JWST reveals, behind every young cluster of stars burning at the dawn of time, there is a quiet story told not by the galaxies themselves, but by the light that escapes from them. And that is where the real journey begins. Because the light we see from the early universe is not the light that was originally emitted. It is stretched, softened, elongated by the expansion of space. It is reshaped by time itself. This stretching is what we call redshift. It is not just a change in color. It is not just the universe adjusting the hue of a distant galaxy. Redshift is the imprint of cosmic history, written directly onto the wavelength of light. So, when we look at Momi Z14 and see its photons dragged into the deep infrared, we are witnessing the universe's expansion sculpting light across more than 13 billion years. The light becomes a kind of relic, a fossil of wavelength, telling us not only where the galaxy is, but what the universe was doing while the light traveled. And, the mechanism is beautifully simple and profoundly strange. Light does not stretch because it tires. It does not fade because it loses energy through the void. The universe expands, and as space expands, it drags the wavelength of light along with it. Well, you see, imagine a wave painted onto a rubber band. As the band stretches, the wave stretches with it. Peaks drift apart. Color shifts. And the wave carries with it a record of how much the rubber has expanded. Light behaves in exactly this way. It is not moving through an empty stage. It is moving through the stage as the stage itself grows larger. So, the light we see from ancient galaxies is not a simple beam traveling outward. It is a witness carried by the expanding cosmos, reshaped with every passing billion years. The fascinating part is that this stretching does not occur because the galaxy moves away like a rocket. At the earliest epochs, the galaxies barely existed yet. It is not motion through space, it is motion of space. And that is why redshift becomes the most powerful tool we have for measuring cosmic time. The bigger the redshift, the farther back in history we are seeing. And the redshift of 14.44 that reveals Momi Z 14 places it in a time when the universe was still a child, still learning how to build the first complex structures. And, this is also why galaxies that old are invisible to telescopes like Hubble. Hubble sees mainly visible and ultraviolet light, but the visible light from early galaxies has been stretched far into the infrared. Their ultraviolet glow has been dragged into colors our eyes cannot detect. So, Hubble could only stare into darkness, seeing nothing where entire galaxies were burning brightly. The universe hid its earliest chapters behind a veil of stretched light. Well, you see, JWST was built to remove that veil. Its mirrors collect infrared wavelengths. Its sensors are chilled to near absolute zero so they can detect faint photons that have traveled for nearly 14 billion years. It is not just a telescope. It is an instrument tuned to the language of ancient light. And that is why the phrase time machine is not a metaphor. It is literal. JWST looks not across distance, but across epochs. When its golden mirrors collect infrared spectra from a galaxy at redshift 14, it is seeing the universe as it existed when stars were new, when gravity was sculpting the earliest forms of structure. And the more you think about this, the more astonishing it becomes. Because time is not like a river flowing around us, separate from our lives. Time is part of the light. It is carried within the wavelength. The deeper the redshift, the older the memory. So, the light that falls into JWST's detectors is history itself. And, that raises a quiet philosophical question. If light carries the memory of expansion, does darkness carry memory too? The first hundreds of millions of years after the Big Bang, the so-called Dark Ages, left no starlight, no galaxies, no luminous record. The only way we will ever understand that era is through the stretching of the cosmic microwave background and the subtle patterns imprinted on its surface. Well, you see, redshift also explains why the cosmic microwave background is now so cold. It was once a blazing wall of radiation. But expansion has stretched its wavelengths into microwaves and cooled them to just a few degrees above absolute zero. And that means the universe's earliest light is still here, still washing across us, still whispering the memory of creation. But for galaxies like Momiza 14, the story is different. Their light was born already within stars. It passed through dust, gas, shock waves, collisions, and then it began its long journey outward. Each year, each century, each eon, the universe expanded a little more, and the light stretched a little more. So, by the time it reached us, that light was not just old, it was transformed. And, well, this transformation reveals something important. Light is not immune to the universe. It is shaped by it. And in being shaped, it becomes a messenger. The story is not just in the galaxy. It is in the light itself. The physics of this stretching is rooted in general relativity. In Einstein's vision, space-time is not a passive stage. It bends, flows, curves, stretches. Light always travels the straightest possible path, but what straightness means depends on how space-time is shaped. And in an expanding universe, straight lines stretch, and light stretches with them. This is why the earliest galaxies appear redder than they should. Not because their stars are cooler, but because the universe has stretched their light over billions of years. It's not just color change, it is aging. The universe ages its own light. And, that leads to one of the most beautiful aspects of redshift. It means that every photon is a message not just from a distant point in space, but from a distant moment in time. When we observe a galaxy at redshift 14, we are not seeing it as it is now. We are seeing it as it was then. Frozen, preserved. A living memory of the cosmos. Well, you see, this allows astronomers to reconstruct the history of the universe without ever leaving Earth's orbit. The universe gives us a record of its own past in the form of stretched waves. And JWST, by reading those waves, reads the early universe like an ancient manuscript. Consider the spectrum of a distant galaxy. The lines, hydrogen, helium, oxygen, are not where they should be. They are shifted downward, redder, longer. And by measuring exactly how far they have moved, we can calculate precisely how long the light has traveled. We can measure the expansion rate. We can measure cosmic time. So, redshift does more than tell us distance. It tells us velocity. It tells us age. It tells us growth. And that is how we know MOME Z14 comes from the epoch when the universe was only a small fraction of its current age. It is how we know the galaxies. Hubble could not see were once bright with ultraviolet. It is how we distinguish ancient from modern, early from late. And there is something poetic in this, because redshift transforms the universe into a timeline. The farther out you look, the farther back you travel. And each galaxy at higher redshift is not just more distant, it is more ancient. And, this is why looking at redshift is like reading a cosmic autobiography written in starlight. Well, you see, all of this leads toward a crucial truth. JWST's ability to detect deep infrared light allows us to see the universe's earliest phases not as abstractions, but as images, as landscapes, as structures. And as we interpret those images, we uncover puzzles. Galaxies that form too early, stars too bright, black holes too massive. And that tells us that redshift is not just a measurement, it is a doorway. Redshift shows us what should not exist, or what should not exist yet. And those impossibilities invite us deeper into the mysteries of cosmic formation. So, as we move forward, the next question arises naturally. If redshift reveals galaxies forming too fast, too brilliantly, too soon, then what do those galaxies actually look like? How large are they? How massive? How unexpected? And that, leads us directly into the next chapter, into the galaxies at 300 to 500 million years after the Big Bang. Galaxies too bright and too heavy for their age. The galaxies that JWST is now forcing us to rethink from the ground up. And, when we step out of the quiet wonder of redshift, with its stretched wavelengths and its gentle reminders that light carries memory, we find ourselves entering a far more turbulent chapter of the universe's story. Well, you see, the deeper JWST looks, the more it reveals something we were not prepared for. Not just early galaxies, but galaxies that are too early. Not just bright galaxies, but galaxies that are too bright. And that is the unsettling beauty of this new cosmic age. Everything is happening too soon. Take a moment and imagine the universe at 300 to 500 million years old. We grow older, clocks tick, but in the grand cosmic chronology, this is still the first breath, the earliest stirrings. Stars have only just begun to ignite. Clouds of hydrogen and helium are collapsing for the first time. And yet, JWST is finding galaxies in this epoch that look as though they belong billions of years later. That is the mystery. So, what exactly is being discovered? Galaxies with masses that rival the modern Milky Way. Galaxies glowing with the luminosity of thousands of supernovae. Galaxies that, by all accounts, should not exist yet because the universe simply has not had enough time to build them. And, the more of them JWST finds, the more it feels as though the early cosmos was racing, sprinting, building itself with an urgency we never imagined. Well, you see, in the classical picture of galaxy formation, everything begins gently. Tiny clumps of dark matter attract gas. The gas cools. Stars form slowly. Over hundreds of millions of years, these proto-galaxies merge and grow. The process is gradual, steady, patient. But the galaxies JWST is showing us are not gradual. They are not patient. They seem to leap out of the void, fully grown. This is where the term too massive appears everywhere in the data, because some of these galaxies are 10 or even 20 times larger than they should be for their cosmic age. Their stellar masses suggest star formation efficiencies that defy the physics we use to model the young universe. So, either the universe formed stars far more efficiently in its early epochs, or our models of gas cooling and gravitational collapse are missing something essential. And, well, the first hypothesis is tempting. Perhaps the early universe was simply better at making stars. Perhaps temperatures and densities aligned perfectly. Perhaps turbulence accelerated collapse. But the numbers, the sheer scale of the luminosity, suggest something even deeper. That conditions in the early universe were not just different, but fundamentally different. The densities were higher. The gas was pristine. Radiation backgrounds were lower. And under those conditions, star formation might have reached efficiencies we no longer see. It's not just star formation being faster. It's star formation being furious. And, then there is the second hypothesis, that dark matter behaved differently at early times. Well, you see, dark matter is the hidden architect of galaxies. It creates the scaffolding on which normal matter gathers. And if the shape of that scaffolding, or the way it clumps, differs from our simulations, then galaxies could grow far more quickly than we expect. Maybe dark matter was more concentrated. Maybe its distribution was more chaotic. Maybe the initial conditions after the Big Bang seeded structures earlier than our models assume. And then, of course, there is the third possibility, the one nobody likes to admit too loudly, that our entire model of galaxy formation, elegant and cherished though it is, may need rewriting. Not destruction, not abandonment, but refinement. Because JWST, with its infrared vision, is revealing a universe that is not contradicting science, but expanding it. And that is always how science grows. Through contradiction, through surprise, through data that refuses to fit. So, what do these two massive galaxies actually look like? When JWST observes them, they are often small in physical size, compact, dense, glowing intensely from the inside. Their light is dominated by the youngest, hottest stars. Their infrared signatures suggest rapid bursts of formation, building stellar mass faster than any model predicted. And what's more unsettling is that there are many of them. Not one anomaly, not two, but a growing family of early giants scattered across the deep field images. It's not a glitch in the data. It's a pattern. And, this leads us into a deeper cosmic truth. The early universe was not calm. It was not quiet. It was not gentle. It was violent, chaotic, rushing forward with a speed we did not expect. Galaxies collided frequently. Gas clouds collapsed quickly. The gravitational landscape was sharp, steep, clumpy. Well, you see, this chaotic environment may have accelerated the growth of galaxies far beyond our estimates. Imagine a universe where everything is closer together, where matter is dense, where distances are small. In such a universe, mergers happen constantly. Galaxies collide and combine. Gas clouds compress violently, and star formation ignites in enormous bursts. So, perhaps these massive early galaxies are simply the result of cosmic proximity. the result of a universe still hot and compact. But, there is a subtle problem. Some of these galaxies are too bright even if we assume perfect efficiency, even if all available gas formed stars. They surpass the theoretical limits of how much luminosity a young galaxy can produce. And that is why astronomers are asking whether something else is happening inside these early galaxies. Something hidden, something powerful. Well, you see, one idea gaining traction is that many of these galaxies contain early black holes, growing rapidly, feeding greedily, emitting enormous amounts of radiation. These black holes could dominate the infrared light we see, making galaxies appear brighter and more massive than they actually are. It's not just stars lighting these early giants, it's black holes. But this explanation has its own puzzles. If black holes were already large at 300 million years, then how did they form so quickly? How did they grow? What seeds did they begin with? So, the mystery multiplies. Each explanation invites a new question. And, this is what makes the JWST era so thrilling. We are discovering a universe that is not a simple extrapolation of what we already know. It is a universe with its own childhood, its own rules, its own logic. The galaxies we see at redshift 10 or 12 are not behaving like scaled-down versions of modern galaxies. They are behaving like something else entirely, something primordial, something fierce and unrestrained. And in a way, this forces us to confront our assumptions. We thought galaxies grew slowly, but maybe they grew in leaps. We thought dark matter shaped them passively, but maybe dark matter sculpted them aggressively. We thought star formation was gradual, but maybe it was explosive. Well, you see, the early universe is not a quiet prelude. It is a roaring overture. And that brings us to the deeper philosophical point. These discoveries are not mistakes. They are opportunities. They are the universe inviting us to understand more, to adjust our models, to refine our theories. And as we gather these luminous anomalies into one picture, we see something emerging. A pattern of formation that suggests the cosmic dawn was not a gentle sunrise, but a blazing flash. Galaxies forming in rapid bursts, black holes growing in sudden leaps, dark matter collapsing in sharp, dense knots. So, what does this mean for our model of the universe? Do we adjust the physics of the early cosmos? Do we modify the behavior of dark matter? Do we reconsider cooling rates, feedback processes, radiation backgrounds? And, perhaps the answer is all of them. Well, you see, science often moves forward, not through perfect predictions, but through anomalies, through objects like these early galaxies that refuse to fit. They force us to rethink, to rebuild, to evolve our understanding. And the beauty of it all is that JWST is still only at the beginning of its mission. These two massive galaxies are likely the first hints of an early universe more dramatic than we imagined. And as JWST looks deeper, it may find galaxies even brighter, even earlier, even more impossible. And that, leads us naturally toward the next mystery. Because some of the most puzzling objects JWST has revealed are not the massive early galaxies, but something stranger, smaller, more intense. The little red dots, tiny galaxies, too bright, too red, too compact. Objects that look nothing like what our models predict. And so, as the early universe continues to surprise us, our journey must move toward them next. And, as we drift from those impossibly massive early galaxies, The ones that formed too fast and too bright. Something even stranger begins to take shape at the very edge of JWST's vision. Well, you see, if the early universe was a wild, luminous storm, then hidden inside that storm are sparks so compact, so intense, so red, that they almost look like cosmic embers. They are tiny, but they burn with an unreasonable brightness. They are small, but they behave like giants. And that is why astronomers have begun to call them little red dots. The name sounds almost playful, but the reality is anything but. The little red dots, LRDs for short, may be among the most confusing and transformative discoveries JWST has made so far. So, what exactly are they? In JWST's deep field images, they appear as small, faintly blurred circular points glowing deep red. Not the red of nearby stars, not the red of dust, but the stretched, ancient red of infrared light that has traveled across nearly 14 billion years. And, the first mystery is their size. These objects are tiny, not just slightly small, but astonishingly compact. Some are only a few hundred light years across, barely larger than a star cluster. Yet, the amount of light they emit suggests that something inside them is burning far more intensely than expected. Well, you see, this is where the second mystery appears. Brightness. They are too bright. Too bright for galaxies of their size. Too bright for the amount of mass they seem to contain. Too bright for the early universe, which should still be assembling stars slowly, cautiously, uncertainly. And then there is the third mystery. Color. They are drenched in deep red. Not just cosmological redshift, but an intrinsic redness that implies either extreme compactness, extreme obscuration, or extreme heat. So, when astronomers look at them, they see not just small red sources, but contradictions wrapped inside contradictions. The leading theories fall into two broad possibilities. And, well, the first is both thrilling and unsettling. The little red dots may contain black holes. Not just black holes, but supermassive black holes. Monsters millions of times the mass of the Sun, embedded inside galaxies barely large enough to host them. It's not just unusual, it's almost backwards. The relationship we see in the modern universe, where massive galaxies cradle black holes at their centers, is inverted. Here, the black hole may be the dominant mass, and the galaxy merely an afterthought. Imagine that. A tiny galaxy with a black hole so massive that it dictates the entire structure. Light from the surrounding accretion disk would be redshifted and obscured, creating the intense, concentrated glow JWST detects. High-energy radiation trapped behind gas clouds would redden the spectrum further. And the size difference alone, that mismatch between a giant black hole and a miniature host, would make the whole system pulse like a cosmic siren. And, that would explain the brightness, too. Black holes feeding rapidly emit enormous energy. If an early black hole were consuming matter at extreme rates, it could outshine an entire galaxy. But, if this explanation is correct, a new dilemma appears. How did such massive black holes form so soon? How did they grow so quickly? What seeds did they begin with? We do not have the answers yet. And that is why the little red dots shake the foundations of early universe theory. Well, you see, the second main explanation is no less extraordinary. Perhaps the little red dots are not powered by black holes at all. Perhaps they are clusters of stars, so densely packed that hundreds of millions of them inhabit a region barely the size of a modern globular cluster. These stars could be extremely young, extremely hot, and extremely metal poor. Their combined radiation could generate the intense, compact glow JWST sees. Imagine a primordial starburst region, a kind of cosmic furnace where every cubic light-year contains thousands of stars. Stars forming in such frenzied density that light cannot escape cleanly. Dust so thick that only infrared wavelengths survive. A cradle of chaos, glowing red from compressed heat. And this explanation has its own consequences. If the little red dots are star clusters pushed to their physical limits, then star formation in the early universe may have behaved far more violently than any model has predicted. The first galaxies may have been compact star factories, forming stars in bursts so intense that modern physics struggles to replicate them. So, which explanation is correct? The truth is that we do not know yet. JWST's instruments give hints, shapes, colors, spectra, but not the full story. Some LRDs show signs of heavy ionization, pointing toward black holes. Others show stellar signatures. Still others show both, as though the early universe refused to pick a single path. And, perhaps that is the real message here. The early universe may not have been tidy. It may not have followed a single rule. It may have produced black hole-dominated galaxies and starburst-dominated galaxies side by side, like competing experiments in cosmic evolution. Well, you see, this is what makes the little red dots so fascinating. They force us to question a basic assumption, that galaxies grow their black holes slowly over billions of years. But what if the universe sometimes worked the other way around? What if black holes helped galaxies form, not the other way? What if early galaxies were born around black holes, like pearls, forming around grains of sand? And inside this possibility lies a deeper symmetry. The modern universe is calm. It is structured. It is predictable. But the early universe was not calm. It was not structured. It was not predictable. It was improvisational. And the little red dots might be the fossils of that improvisation. And, there is another thread emerging from the data. Many LRDs lie at redshifts around 7, 8, 10, periods when the universe was only a few 100 million years old. These objects appear suddenly, almost explosively, in the JWST deep fields. They are not rare exceptions. They are a population. The implication is profound. Whatever created them was not a fluke. It was a fundamental part of cosmic evolution. And that means our picture of galaxy formation must be updated, not replaced, not torn down, but expanded. Because LRDs show us that the early universe built structures at two extremes: enormous galaxies that formed too fast, and tiny galaxies that shine too brightly. Well, you see, this duality is not a contradiction. It is a hint that something deeper shaped the early cosmos, perhaps the density of matter, perhaps early turbulence, perhaps quantum fluctuations inherited from inflation, or perhaps, and this is the most intriguing possibility, black holes themselves seeded structure. If a black hole forms early, its gravity anchors gas, pulling matter inward rapidly. This could create a compact, high-pressure disk where stars form at extraordinary rates. In this view, the little red dots might not be anomalies but the first building blocks of massive galaxies. Well, if the LRDs are instead starburst clusters, then they show the opposite truth. That early star formation did not require black holes at all. Instead, gas clouds may have collapsed under their own density, forming stars at efficiencies far beyond what we see today. So, the universe may have followed two parallel paths: black hole-driven growth and gas-driven growth. And the little red dots sit at the intersection, blurring the line, reminding us that early cosmic evolution might not be monolithic. And, as we puzzle over these objects, we begin to sense that they might be connected to another mystery, a deeper one. The mystery of early black holes that appear too massive for their age. Well, you see, some of the LRDs may actually be the seeds of those later giants. If a little red dot contains a tiny galaxy wrapped around a rapidly growing black hole, then in a few 100 million years, that system could become one of the monstrous black holes JWST detects at later cosmic epochs. In that sense, the LRDs are not the end of the story. They are the beginning. They are the first pages of the chapter on black hole formation. And, if we follow that path, we arrive at one of the most astonishing puzzles of the JWST era, the discovery of black holes feeding at rates we previously believed impossible. Black holes devouring matter 40 times faster than the so-called stable limit. So, this is where the little red dots lead us, into the realm of early black holes consuming the universe in great luminous gulps. And that, is exactly where our next chapter must go. Toward the supermassive black holes of the early universe, larger, hungrier, and more impossible than anything we expected to find. And, when we step from the faint ember glow of the little red dots into the deeper darkness that surrounds them, we find something even stranger flickering at the edges of cosmic history. Well, you see, if the little red dots were the first whisper of a hidden population, then what JWST uncovered next, the LRDZ86 class, feels like a declaration, a revelation, a message written across the earliest light. The universe was feeding its black holes faster, harder, more violently than any theory ever dared to predict. The LRDZ86 object is small. It is tiny. It is almost nothing. A bright red speck in the abyss. And that is what makes it astonishing. Because its light does not behave like the light of a star cluster. It does not behave like the youthful blaze of newborn galaxies. The spectrum reveals extreme ionization, extreme heating, radiation signatures so sharp and so intense they feel like cosmic sirens. They point to one thing: a black hole growing at a rate that should be impossible. So, let's follow that thought for a moment. We know black holes can only feed so fast, at least according to the classical picture. The so-called Eddington limit, the balance between inward gravity and outward pressure of radiation, says that a black hole cannot consume matter past a certain speed. If it tries to swallow more, radiation pushes the infalling gas away, slowing the process. Well, you see, this limit is supposed to be universal. Ironclad, a barrier rooted in the mathematics of light and gravity. But LRDZ86 does not seem to care. The black hole inside it appears to be feeding at 10 times, 20 times, even up to 40 times the Eddington limit. That is not just unusual. It is extraordinary. It is the kind of behavior no one expected to see in the first few 100 million years of cosmic time. It means black holes in the early universe grew like wildfires, with none of the restraint imposed by the modern cosmos. And, the data is relentless. The object is compact, redshifted, ionizing its surroundings with brutal intensity. The radiation is too hard for stars alone, too sharp, too hot. So the most straightforward explanation is a black hole swallowing matter at ultra-fast rates. But, If that is true, if black holes grew 40 times faster than our equations allow, then every model of early galaxy formation must be adjusted. Not just tuned, not just refined, rethought. Because the early universe appears to have been a factory for black holes, factories that operated with a reckless efficiency. The obvious question is, how? How can a black hole bypass a universal limit? How can gravity win so decisively against radiation? The leading idea is that dense gas in the early cosmos collapsed so quickly, so violently, that the black hole was buried under a blanket of infalling matter. Radiation could not escape, and if it cannot escape, it cannot push back, and if it cannot push back, the black hole is free to gorge itself in great luminous gulps. Well, you see, the early universe was thick with gas, unpolluted, pristine, rich with cold hydrogen. Dense environments like that would suffocate radiation. The black hole becomes a kind of cosmic furnace sealed inside an opaque cocoon. And, trapped radiation no longer sets the limit. Feeding becomes unbounded. And this explanation leads naturally to the next question. Where did the seeds come from? How did the first black holes appear so early? So massive, so ready to feed? So, we turn to the second class of objects JWST revealed, LID 568. On the surface, it is just another faint, red, compact dot. But when its spectrum was analyzed, something astonishing emerged. The source emits light brighter than any star cluster of its size should. The gas around it is overheated, over-ionized, and the signature, once again, matches a black hole consuming matter at extreme, super Eddington rates. And, well, the implications ripple outward. If LID 568 contains a black hole of tens of thousands, perhaps hundreds of thousands of solar masses, then that black hole formed almost immediately after the first stars ignited. This is not gradual growth. It is not slow accumulation. It is a leap, a cosmic leap. The theory that can explain this is known as direct collapse. Instead of forming from the deaths of the first stars, the black hole forms directly from the collapse of enormous gas clouds, clouds so massive and so cold that they skip the star formation stage entirely. A whole region of space collapses inward and forms a black hole seed already 100,000 solar masses. Imagine that. A starless birth. A black hole born fully grown. Not just a remnant of a star, but a direct child of cosmic gravity. Such seeds would have a head start, allowing them to become supermassive black holes in only a few 100 million years. And, this is precisely what JWST seems to be glimpsing. Direct collapse seeds. Monsters from the beginning. The giants that would later anchor quasars. The giants that would sculpt the earliest galaxies. But, well, even direct collapse cannot solve everything, because these seeds still need to grow. They still need to feed. And LRDZ86 and LID 568 show feeding that is not just strong, but extreme. The early universe must have been a place where gravity and gas density allowed black holes to feed far beyond theoretical limits. And as we put all this together, a pattern begins to form. The earliest galaxies were not just cradles for stars. They were also engines for black holes. In some cases, the black holes may have come first, not just shaping galaxies, but defining them. And the more you think about it, the more beautiful and unsettling the picture becomes. Black holes, objects we once believed were silent, passive, waiting for matter to fall inward, turn out to be the architects of early cosmic structure. They are not just endpoints of stellar evolution. They are the seeds of galaxies. They are the gravitational hearts around which the earliest systems assembled. So, the early universe may have been a place where black holes flourished like living things, where they grew in bursts, where radiation pressure could not stop them, where dense gas collapsed so violently that entire regions of space were consumed into gravitational singularities. And that reshapes the way we understand the cosmos. Well, you see, when black holes can feed at 40 times the Eddington limit, timelines shrink. Growth accelerates. A black hole that would take billions of years in the modern universe could reach supermassive size in a fraction of that time. This explains the quasars JWST sees at redshifts 10, 11, even 12. Quasars powered by black holes a billion times the mass of the Sun, already shining when the universe was less than a billion years old. These were once considered impossible. And now, JWST shows us that they were not rare. They were not exceptions. They were part of the early architecture. The universe produced black holes the way storms produce lightning, suddenly, violently, repeatedly. And, there is a philosophical beauty here. It's not just that black holes grew quickly. It's not just that they fed beyond expected limits. It's that the early universe behaved differently from the world we know now. Not just in degree, but in nature. It is not just older, it is stranger. The story begins to look like this. The first stars ignite. Some collapse into black holes. Some regions collapse directly into black holes. And those black holes feed in supercharged bursts, releasing radiation that reshapes gas, triggers star formation, sculpts the first galaxies. So, instead of galaxies forming first and black holes forming later, the universe may have built them together. Not just galaxy growth, but co-growth. Not just stellar evolution, but black hole evolution. And, as these ideas settle, a new question emerges quietly, but inevitably. If early black holes fed at super Eddington rates, then what did this feeding do to the surrounding gas? How did it shape the structure of early galaxies? Did it choke star formation or ignite it? Did it sculpt cosmic flows, carve cavities, heat filaments? Well, you see, this leads naturally into a broader concept, one that ties galaxies, black holes, and cosmic evolution together. Feedback. And that, is where our journey must go next, toward the ways black holes, through their violent feeding, transformed the early universe, not just by growing themselves, but by altering everything around them. And, as we drift away from those early black holes feeding in the dark like cosmic furnaces, something else rises from the shadows of the young universe. Something louder, something more violent, something carved not by steady growth, but by collision. Well, you see, if supermassive black holes grew far faster than expected, then perhaps they did not grow alone. Perhaps the early universe was not a place of solitary giants, but a realm where galaxies themselves collided, merged, and tore through one another in great luminous storms. And that is where the story of mergers begins. The image that captures this truth most clearly is one JWST revealed, and scientists labeled ZS7. At first glance, it looks like a smudge, a swirl, a pair of faint lights leaning toward each other across the cosmic night. But when the data is peeled apart, when spectra, redshifts, ionization levels, and velocities are examined, the truth reveals itself. These are not stars. These are not clouds. They are two galaxies merging, and at their hearts are two black holes spiraling inward, closing the distance between them only 740 million years after the Big Bang. So, think about that for a moment. Two supermassive black holes, already formed in less than 1 billion years, are now plunging toward merger. We once assumed mergers like this required the long, slow evolution of the mature universe. We assumed they belonged to later cosmic epochs, when galaxies were large and the gravitational choreography more stable. But JWST shows that the early universe did not wait. It collided early. It collided violently. It collided often. And, the ZS7 system is not just a merger. It is a revelation wrapped inside a collision. The velocities of the two galaxies indicate they will merge fully in only a few million years. A blink in cosmic time. Their black holes, already massive, will join into a single monster, a seed that could eventually become one of the billion solar mass quasars JWST sees at redshifts 10 and 11. So the growth problem we struggled with earlier, the impossibly large black holes forming too soon, suddenly becomes more than a puzzle. It becomes a pattern, a path. Well, you see, mergers offer a shortcut. Not just adding mass, but multiplying it. Two black holes do not grow linearly when they merge. They leap. They skip steps. They jump forward in the timeline. And in a universe as dense and crowded as the early one, mergers were not rare exceptions. They were the rule. The universe was smaller then. Distances were shorter. Galaxies were packed tight like sparks inside a cosmic furnace. And so, when they moved, even slightly, gravity dragged them inward toward one another. The beauty of ZS7 is that it shows us this process frozen in ancient light. The two black holes, each wrapping space around themselves, distort their surroundings. Gas funnels inward. Stars are whipped into chaotic orbits. Shock waves ripple through interstellar matter. Radiation erupts from accretion disks so bright that JWST can detect it across more than 13 billion years. And that is the astonishing part. Not just that mergers happened, but that we can watch them happening. And, well, this raises a profound thought. The early universe did not grow through slow, patient accumulation. It grew through collision, compression, and combination. Galaxies smashed together, creating new structures as quickly as they destroyed the old. It's not just that mergers accelerated growth. Mergers defined growth. And yet, we must be careful. Not every luminous object in the early universe is the result of a merger. Not every intensely bright region hides two black holes spiraling inward. But the frequency of these events, the number JWST is revealing, suggests they played a far more central role in shaping early cosmic architecture than we ever imagined. And, this is where the cosmic story widens. Because mergers do not only enlarge black holes, they reshape galaxies. They trigger star formation. They ignite bursts of energy that blow gas outward or pull it inward. They scramble orbits, fuse dark matter halos, and establish the gravitational skeletons of future galactic structures. Well, you see, the Milky Way itself is the result of countless mergers. Our stars, our planets, our atoms, everything that formed our cosmic home, comes from the wreckage of ancient collisions. And in the distant future, far beyond the time of 2025, another great merger awaits us, the collision between the Milky Way and Andromeda. Consider that for a moment. Two great spirals drifting toward each other across empty space. Two behemoths held by gravity's soft hand, drawing closer by a few tens of kilometers every second. One day, though long after humanity is gone, their disks will overlap. Their stars will scatter like embers. Their black holes will fall inward, orbiting each other in a slow but inevitable dance. So, the merging we see in ZS7 is not alien to us. It is not foreign. It is the past and the future of our own galaxy. And this is why the discoveries JWST makes do not simply expand our knowledge of the early universe. They reflect something deeply personal. We are children of collisions. Our galaxy was forged in violence. Our sun was born from the debris of merged star-forming regions. The atoms in our bodies were cooked in stars that died, were reborn, and collided again inside younger galactic structures. But ZS7 offers something else, something we rarely glimpse. It shows two black holes not after merger, not long after the fact, but in the process of merging. And merging black holes produce ripples, not in light, but in space-time itself. Gravitational waves. Waves that echo across the fabric of the universe. Well, you see, this means the early universe must have been filled with gravitational waves. Not isolated events, but a continuous background of ripples generated by merging galaxies, merging black holes, merging structures of all kinds. And although our modern detectors, like LIGO and Virgo, catch only the loudest, nearest events, future observatories may detect the deep background hum of these ancient collisions. And that is the poetic twist. Even now, the universe may still be vibrating faintly from the mergers of the first billion years. Imagine that for a moment. A universe ringing like a bell struck in its infancy. A hum stretching through time. A rhythm woven into the very geometry of space-time. And, ZS7 is one of the first clear visual confirmations that these early collisions occurred far earlier and far more frequently than we expected. The details from JWST show gas streams connecting the two galaxies, show tidal distortions, show velocity shifts implying gravitational interaction. These are the fingerprints of merger. And wrapped inside this interaction is the evidence of two black holes, each lighting its own region with heat, ionization, and radiation. The gravitational centers of the two systems are offset. The spectra reveal two distinct sources of hard radiation, and the surrounding gas is carved into shapes that only a double nucleus can create. So, this is more than a chance alignment, more than a coincidence. This is a merging galaxy system, caught in the act, and its significance is immense. And, well, when we consider all these observations together, we begin to understand that mergers are not just part of the story of early black hole growth. They are essential to it. They are accelerators. They are catalysts. They do not simply add mass. They amplify growth. They create instabilities that funnel gas inward. They trigger starbursts that enrich and redistribute material. They clear pathways for black holes to collide. Well, you see, if the early universe was chaotic, then chaos was not a side effect. It was the engine. It was the mechanism by which complexity arose. Disorder produced order. Violence produced structure. Collision produced creation. And that realization is both humbling and beautiful. We like to imagine the cosmos as serene, elegant, governed by soft forces and slow changes. But the early universe was not serene. It was a storm of matter, light, and gravity. And from that storm emerged the galaxies that later matured into the spirals, ellipticals, and dwarfs we see today. And as JWST continues to scan the deep fields, it will find more ZS7 systems, more merging black holes, more flickers of ancient violence. Each of them a clue, a fragment, a fossil in light, and, as we follow these clues, a new question begins to take shape. If mergers drove the rise of early supermassive black holes, then how did this interconnected web of collisions reshape the universe during the era known as the cosmic dawn? How did these turbulent structures bring light back into a universe that had been dark for hundreds of millions of years? Well, you see, that transition from darkness to light, from cold silence to brilliant starlight, is one of the most profound in cosmic history. And so, our path leads naturally to the next chapter, the birth of the first stars, the end of the Dark Ages, and the Ryanization of the cosmos. And, as we drift away from the violent dance of merging galaxies, from those spiraling black holes devouring the young cosmos, we begin to sense a deeper silence beneath the chaos, a silence older than starlight itself. Well, you see, before the universe burned bright, before any galaxy existed, before even the faintest spark ignited hydrogen into flame, there was a period of profound darkness, the Dark Ages, a time when space was filled not with light, but with potential. And that is where the next chapter of our journey must lead. Imagine the universe just after the Big Bang. It is hot, dense, radiant. But as it expands, it cools. Protons and electrons meet and bind into neutral hydrogen, and with that union, the universe goes dark. So, for millions upon millions of years, the cosmos becomes invisible. No stars, no galaxies, no light. Just a deep, cosmic night stretching across the entire sky. The hydrogen fog filling space absorbs every photon. Nothing escapes, nothing glimmers. It is a silence so complete that even time feels suspended. And, this darkness lasted far longer than most people realize. Hundreds of millions of years. We grow older. Clocks tick. Stars are born and die inside our imaginations. But the early cosmos simply waited. Quiet. Cooling. Preparing for the first sparks. Well, you see, the end of this darkness, the moment the universe's first light returned, is what astronomers call the cosmic dawn. And this dawn was not a sudden sunrise. It was fragile. It was scattered. It began with the very first stars, the so-called population 3 stars, enormous giants made almost entirely of hydrogen and helium, unpolluted by heavier elements. Stars so massive they burned with a ferocity the modern cosmos cannot replicate. These first stars ignited inside dense pockets of gas. When they lit up, their ultraviolet radiation carved bubbles of ionized hydrogen around them, small pockets of transparency within an ocean of darkness. And, as more stars formed, more bubbles grew. They overlapped, merged, expanded. This slow, patchy process is what we now call reionization, the moment the universe regained its transparency. So, Ryanization is not just a technical term. It is the story of how the universe learned to shine again. And that is precisely what JWST is now seeing in exquisite detail for the first time in human history. In the deep fields JWST observes, we see galaxies whose light is not smooth, not clean, but sculpted by the fog around them. Their spectra reveal massive amounts of neutral hydrogen still absorbing the earliest photons. The patterns in their emission lines show us that they lived at the frontier between darkness and light, half hidden, half revealed. It's not just that JWST sees galaxies, It sees galaxies struggling to illuminate the universe. And, well, this is where the data becomes astonishing. Some galaxies at redshift 9, 10, even 11 show evidence of carving enormous ionized bubbles around themselves. These galaxies were small, fragile, often only a few 100 million years old, and yet they reshaped regions of space tens of thousands of light years across. Not just objects in the universe, but sculptors of it. Well, you see, this means the earliest galaxies were far more efficient at producing ionizing photons than we assumed. Their stars were hotter, their star formation rates were higher, their environments more extreme, and their radiation, sharp, intense, relentless, began dissolving the cosmic fog. And the deeper JWST looks, the more complicated the story becomes. Because the galaxies alone may not have been enough to reionize the universe. Some of the ionizing power may have come from smaller structures, protoclusters, dense star-forming knots, or even primordial black holes radiating intensely through accretion bursts. So, the cosmic dawn was not the work of a single type of object. It was a chorus. Massive galaxies, tiny red dots, supermassive black holes, violent starbursts, all contributing photons into the dark sea of hydrogen. And, as these sources carved channels through the fog, the universe slowly brightened. First in isolated pockets, then in networks, then everywhere. The moment ionization finished, the universe became transparent to ultraviolet light. Suddenly, starlight could travel freely. Galaxies could shine across billions of light years. Photons could escape the gravity wells in which they were born. And in that transition, from opaque to transparent, from cold to luminous, the universe became the universe we know today. What JWST is capturing now is not just the light of early galaxies. It is the light that ended the long cosmic night. It is the first illumination, the rekindling, the moment the universe breathed fire for the first time. And, when you look at the spectra of these early galaxies, the hydrogen absorption troughs, the sharp break between ionized and neutral regions, the extended red wings from scattering, you can almost feel the presence of the fog. It is the closest we may ever come to witnessing the night before light existed. Well, you see, this is more than a scientific discovery. It is a philosophical one. It reminds us that darkness is not a void. It is a beginning. It is a womb for creation. And light is something the universe must learn to make. The cosmic dawn teaches us that light is not guaranteed. It is earned. It is constructed. It emerges only when gravity, gas, and time collaborate in just the right way. And, it also hints that the universe's earliest light was shaped and magnified by something we have only begun to understand: gravity itself bending space like a lens. The galaxies of the cosmic dawn were dim, fragile, often too faint for JWST to observe directly. Yet we can see many of them because the universe provides its own magnification. So, as we follow this early light through the stretching fabric of space, our journey naturally turns toward the next mystery: the universe itself as a lens that bends, magnifies, and stretches the light of galaxies, hiding even deeper in the dark. And, as we drift out of the fading glow of the cosmic dawn, as the first stars carve the fog and the universe slowly becomes transparent again, something extraordinary emerges from the expanding darkness. Well, you see, light does not always travel in straight lines. It bends, it curves, it follows the shape of space-time itself. And because the universe is not empty, but filled with clusters of galaxies, with webs of dark matter, with hidden structures sculpting gravity's landscape, that bending becomes one of the most powerful tools we have for looking deeper into the past. And that is where gravitational lensing enters the story. Imagine a distant galaxy, one so faint, so ancient, so fragile that its light alone could never reach us. Between that galaxy and us lies a massive cluster, a great shimmering knot of matter. And when the ancient light approaches that cluster, the gravity pulls on it. Not just a gentle tug, but a reshaping, a focusing, a magnification. So, what we see through JWST is not just a distant galaxy, it is a galaxy stretched and brightened by the universe itself. The cosmos becomes its own telescope. The beautiful part of this is that gravitational lensing works not through mirrors or metal, but through the curvature of reality. Light does not choose its path. Space-time decides it. And JWST, with its exquisite sensitivity, captures the distorted arcs, the smeared crescents, the mirrored copies of galaxies that sit far behind massive clusters. In this way, the telescope sees objects billions of years older than those it could observe alone. And, some of the most distant galaxies ever detected, those at the edge of cosmic visibility, were found only because a cluster magnified their light. Without lensing, they would remain hidden forever. The concept is simple but profound. Mass bends space-time. Space-time bends light. And JWST uses this natural lens to extend its own vision. It is not just a telescope observing the universe. It is a telescope partnering with the universe. Well, you see, gravitational lensing is not just a trick of light. It is a map of matter we cannot see. Because dark matter, although invisible, still bends space-time, still shapes the path of photons, still creates distortions in the images JWST receives. And, well, when scientists study these distortions, how arcs stretch, how magnification varies, how multiple images of the same galaxy appear at different positions, they can reconstruct the hidden distribution of matter. Not just the bright matter, but the dark scaffolding underlying all of cosmic structure. So, gravitational lensing becomes a kind of cosmic fingerprint. The universe leaves clues in the light, and JWST reads them. Take a moment to imagine a massive galaxy cluster, something like 1,000,000 billion solar masses. A gravitational city built from thousands of galaxies. When light from background galaxies passes near it, the cluster acts like a lens with multiple layers, multiple strengths, multiple curvatures. The result: arcs of red, glowing streaks, mirrored pairs, sometimes even perfect rings. Einstein rings. As if space-time itself were performing a quiet magic. And that gives astronomers the chance to study both the lensed galaxies and the lensing cluster itself. A dual vision, a 2-for-1 window into the universe. And, lensing does something else, something subtle. It reveals that the universe is larger than our intuition allows. Because when a faint galaxy is magnified, when its light is stretched across the sky, we suddenly see details. Stellar nurseries, star-forming knots, bursts of ultraviolet light that we never expected to observe from such remote, ancient systems. Well, you see, this transforms our understanding of early galaxies. Instead of tiny, smudged dots, lensing shows them as structures, shapes, places with internal complexity. It is not just that the universe becomes clearer, it becomes more alive. And, the more we observe these lensed galaxies, the more patterns emerge. Some are far brighter than expected. Some form stars at impossible rates. Some appear stretched by cosmic expansion, yet sharpened by gravity, creating a strange duality. The farther they are, the clearer lensing makes them. So, the universe gives us depth by bending light. And JWST, by capturing that bending, becomes not just a tool for seeing, but a tool for measuring. The strength of the lensing effect tells us how much mass lies inside a cluster, how much dark matter, how the invisible skeleton of the universe evolved. These maps are not sketches. They are reconstructions of the very bones of the cosmos. And, in the faint, stretched arcs of ancient galaxies, we find evidence that the universe's structure was already rich and complex at an early age. Dense clusters, massive halos, webs of dark matter pulling galaxies together long before we expected them to form. And this is where lensing becomes more than an observational trick. It becomes a hint that our models of cosmic growth, the speed, the timing, the clustering, may need refining. Perhaps the early universe was denser. Perhaps matter collapsed faster. Perhaps dark matter behaved differently in its youth. Well, you see, gravitational lensing is not just a window. It is a test of cosmology, a test of gravity, a test of the structure of space-time itself. And the deeper JWST looks, the clearer that test becomes. And, well, as we begin to stitch these gravitational maps together, from cluster to cluster, from arc to arc, a pattern forms. A pattern that leads to one of the greatest puzzles in modern cosmology. A puzzle that touches the expansion of the universe, the very rate at which space stretches. So, after lensing shows us the universe as a magnifying glass, the next question inevitably arises. How fast is this expanding stage actually growing? How fast is the universe stretching around us? And that brings us directly to the next great mystery, the Hubble tension, a conflict between measurements. A disagreement at the heart of cosmology. A sign, perhaps, that something fundamental in the universe is missing. And, as we drift away from the cosmic magnifying glass of gravitational lensing, from those arcs of ancient light bending gently through space-time, another question begins to press against the edges of our understanding. Well, you see, once we know how the universe bends light, we must ask how fast the universe itself is stretching. Because beneath every distant galaxy JWST observes, beneath every red arc, beneath every faint whisper of rionized hydrogen, there is an expansion, a stretching of reality. And that leads us directly into one of the greatest puzzles in modern cosmology, the Hubble tension. The story begins with something simple. If the universe is expanding, then galaxies are drifting apart. And the faster a galaxy moves away, the more its light is redshifted. So, we measure that redshift, compare it to the galaxy's distance, and from that we calculate the expansion rate of the universe, the Hubble constant. The remarkable thing is that we have two ways to measure this rate. One looks back to the universe's beginning. One looks at the universe as it is now. And, the trouble begins when these two ways disagree. Well, you see, the first method uses the cosmic microwave background, the faint, ancient radiation left from the universe's earliest moments. It is a relic of a time when the cosmos was only a few 100,000 years old. By studying its temperature fluctuations, cosmologists can infer how quickly the universe must be expanding today. This method gives a slower rate. The second method looks at nearby galaxies, modern galaxies, using standard candles such as Cepheid variable stars or Type 1a supernovae. These objects have known brightness, so by comparing how bright they appear to how bright they should be, we can calculate distance directly. This method gives a faster rate. And that is the problem. The early universe says the expansion today should be slower. The local universe says it is faster, and the difference is not small. It is significant. It is stubborn. It refuses to disappear no matter how carefully we measure. And, well, for years some suspected error, calibration errors, misidentified stars, dust obscuring measurements, uncertain distances. But JWST changed that conversation entirely. JWST revisited the classic Cepheid systems, the ones Hubble studied, and measured them with its extraordinary infrared sensitivity. Cepheids flicker with predictable rhythms, and their brightness in infrared wavelengths pierces dust far more cleanly. So JWST produced measurements so clear, so precise, that the margin of error collapsed. Well, you see, the result was undeniable. The Cepheid method is correct. The local expansion rate truly is faster than the early universe predicts. The tension is real. And, when a tension in physics refuses to go away, it is often a sign that something fundamental is missing. Not just a number, not just a calibration. A piece of the universe. So, what could be missing? Possibilities bloom like distant galaxies. The first is that dark energy, the mysterious presence driving the universe's accelerated expansion, may have changed over time. Perhaps it was weaker in the past and stronger now. Not just a constant, but a dynamic force. And, the second is that dark matter may interact in ways we have never seen. Maybe it clumps differently. Maybe it exchanges energy. Maybe it affects early expansion more than later. And, the third possibility is even stranger. Perhaps there exists a new particle, a new kind of radiation, sometimes called dark radiation, that influenced the early universe but thinned away later. A hidden population shaping the cosmos from behind the veil. Well, you see, each of these ideas would reshape cosmology. They would rewrite the equations of expansion, alter the geometry of space-time, and shift our understanding of how the universe evolved from the cosmic microwave background to the galaxies JWST observes. And then there is the most unsettling possibility, that the model we use, the grand model of cosmology, the one we call lambda CDM, is incomplete. Not wrong, not broken, but missing pieces. Pieces that JWST, in its quiet way, is helping us discover. So, the Hubble tension becomes not a problem, but a doorway, a clue, a signpost pointing toward new physics. And the deeper we look, the stranger the universe becomes. Because JWST reveals galaxies too bright, lenses too strong, structures too early, black holes too massive, and now expansion rates too different. All these anomalies whisper the same thing. The early universe is not as simple as we believed. And this leads us to a philosophical crossroads. Physics thrives on tension. Tension forces refinement, forces honesty, forces growth. The Hubble tension may be telling us that the universe contains more than dark matter and dark energy, more than the known particles, more than the equations of expansion we have stitched together over the past century. Well, you see, when two measurements disagree about something so fundamental as the speed of expansion, the disagreement itself becomes a teacher. It asks, what have we overlooked? What assumptions do we cling to? What symmetry? What particle? What field? Or what entirely new phenomenon waits quietly behind the equations? And the beauty of this tension is that it does not break cosmology. It enriches it. It stretches it. It encourages a new generation of researchers to imagine what else might exist. And, JWST's role in this mystery is profound. It did not cause the tension, but it confirmed it, strengthened it, clarified it. It sharpened the local measurements so precisely that the universe now seems to be whispering, look again, look deeper. The expansion is not just a number, it is a story. A story that began in the cosmic microwave background, grew through the first galaxies, accelerated under dark energy, and continues even now as the universe becomes sparser and colder. So, the question is no longer which measurement is wrong. The question is what new physics lies between them. And, well, as we move forward from this mystery, another puzzle rises quietly behind it. If the universe's expansion rate may contain hidden physics, then perhaps the nature of dark energy itself requires a deeper examination. Perhaps its influence is not constant. Perhaps it evolves. Perhaps it interacts. Well, you see, one mystery leads to another in cosmology. The Hubble tension opens the door. Dark energy waits just beyond it. And that, is where our journey naturally turns next, into the strange, elusive force that shapes the destiny of the universe itself. And when we finally step back from this long journey, from the stretched light of the first galaxies, from the impossible brilliance of the little red dots, from the roaring growth of early black holes and the quiet glow of the cosmic dawn, there is a gentle realization waiting for us. The universe has never been small. It has never been simple. It has never been ordinary. It has always been larger, older, and more complex than the stories we tell about it. JWST does not make the cosmos stranger. It reveals the strangeness that was always there. We thought galaxies would form slowly, yet we found them blazing into existence almost as soon as time allowed. We thought black holes would take billions of years to grow, yet they were already giants before the universe was 1 billion years old. We thought the first structures were fragile and dim, yet lensing shows them stretched across space-time like luminous fossils of creation. And even the expansion of the universe, something we believed we understood, now speaks in two voices, whispering that there is more to reality than our current physics can hold. But this is not a failure of science. It is its heartbeat. Every contradiction is a doorway. Every anomaly is a new horizon. Every piece of impossible data is the universe inviting us to look again. JWST does not break cosmology. It deepens it. It extends the frontier of what we can know while reminding us of how much remains hidden. And perhaps that is the real gift of this golden telescope orbiting far beyond the Earth. It teaches us that the light arriving in its mirrors is not just information. It is history. It is memory. It is the story of everything that has ever existed, traveling for billions of years to reach us. We are not separate from that story. We are woven into it. The atoms in our bodies were forged inside stars that lived and died long before the sun was born. The galaxies we observe are the great ancestors of our own cosmic home. And the expansion that stretches their light also stretches the space through which we live our lives. In that sense, to observe the universe is to observe ourselves, spread thinly across time, delicately connected to events unimaginably distant. So as JWST continues its quiet watch, gathering light older than Earth, older than the Sun, older than the Milky Way itself, we are reminded of something simple and profound. We do not merely study the universe, we unfold with it. And the light that reaches us, after crossing the vastness of cosmic history, is not just a measurement. It is a message, a reminder that we are part of a story still being written, a story as wide as the sky and as ancient as time itself, and that the universe will always be larger than anything we can imagine. Yet somehow still intimate enough to include us within its unfolding dawn.